Hello and welcome to Textbook Engineering Problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition. We're working on problem number 2.42. It says that it's a computer problem. They've got a pretty big table of data here. I'll go ahead and read the problem statement. A published study of a chemical reaction A goes to P indicates that if the reactor initially contains A at a concentration Ca naught in grams per liter, and the reaction temperature T is kept constant, then the concentration of P in the reactor increases with time according to the formula, and they give us the formula here. Cp in grams per liter is equal to Ca naught. This is an exponential decay function. Okay. The rate constant, K, in seconds, inverse, is reportedly a function only of the reaction temperature. To test this finding, the reaction is run in 4 different laboratories. The reported experimental results are given below. This is an exponential function. So we are going to manipulate the function here a little bit. So Cp over Ca naught minus 1 is going to be y, and then e to the minus kt. That's negative. Let's get rid of that negative. So let's flop it. Okay, so let's flip it and say 1 minus Cp over Ca naught equals e to the minus kt. Okay, so that's going to be our y. So let's take the natural log now of 1 minus Cp over Ca naught equals minus kt. Okay, so that means that we can use a plot that goes through the intercept, basically, of a line. So we've got our y equals the natural log 1 minus Cp over Ca naught. Our x is equal to t. Our slope is equal to minus k, and our intercept is equal to 0. So our equation for a line actually looks like this: y equals mx. Okay? So what plot would yield a straight line if the given equation is correct? If we plot this line on rectangular coordinates, then it will yield a straight line. So now in part B, it says enter the given data into a spreadsheet. Okay, so for this next part, we are going to move over to the computer. Okay, as you see here, I've entered in all of the data from the table they gave to us into the computer here. This is the equation they gave to us, and we've converted it into a line, and so we'll have our model that we input for all of these data points, and then we'll calculate what the slope is for each of these data points, for each of these sets of data: lab 1, lab 2, lab 3, lab 4, and so on. Okay, so part B, it says enter the given data into a spreadsheet. We've done that. For each data set, Cp versus T, generate the plot of part A and determine the corresponding value of K. Your spreadsheet program probably has a built-in function to perform a linear regression on the data in 2 specified columns. Yeah, so yeah, it does. I've shown that in several occasions, so we'll just not repeat and go over that again. Okay, so for this next part, we're going to calculate what y is and convert each of these data points into y, and then we'll also have an x column that we need. So let's get a big X column here. So X equals T, so that doesn't change. That's convenient. Okay, Y, on the other hand, changes significantly. It's the natural log of 1 minus Cp divided by the initial concentration. And we want the letter to change, but we don't want the number to change. So let's do that. And drag that down. And let's see if that worked. Yep, that worked. So 1 minus Cp divided by that, okay? And then we want to drag all of these over. And let's check this to see if this worked. Yep. Okay, we've got an error here, and that's because the final concentration here equals the initial concentration of Ca naught. And technically that is not possible. So it's just, you can get very, very close to zero, but according to our equation, there's always going to be just a very, very, very small, you maybe only have one atom left, but there will always be a certain amount of concentration of A left that hasn't reacted. And so having this exact is why we're getting a little error here. And that's no problem. We can just kind of ignore that data point if we need to. Okay, so we have our X and Y axes set up, and it told us to determine what K is for each of these, okay? So let's determine what K is for each of these points. K is the slope. Okay, let's determine the slope first, and then we'll convert it into K. So the slope, we have the known Y's, and we have the known X's. And the X column does not change for any of these, so we'll leave that there. And then we'll just drag that across for each of the labs. We'll have to change this one a little bit so it doesn't have the number error in it. Okay, and yep, those are all looking good. Okay, so now let's convert our K, which is equal to the opposite of the slope. So now we've converted to figure out what K is for each of these. Great. So now we've calculated K. Generate the plot. Okay, so now we're also plotting the data. Use the results in part B to come up with a good estimate of the K value at 275 degrees Celsius. Explain how you did it. Okay. Let's first just plot all this data, because it does say to generate the plot. So let's get our data plots and say data 1, X, Y, okay, then add data 2, X, Y, okay, add data 3, X, Y, okay, now we need to make a model column, so we'll say lab 1, 2, 3, 4, and have our time here, we'll do it over the same time frame, lab equals, now we're using this equation, but we know what K is for each of these values, so we're going to use that function. So Ca naught times 1 minus the exponent minus k times t. And k we want the letter to change but not the number, and t we want the number to change but not the letter. Okay, and that's looking good. Okay, so we'll drag this down and drag this over and take a look. That looks good. And how does this look? We're hitting the wrong concentration, so we want our concentration column to change, our letter to change, but not the number. There we go. Okay, so let's re-drag that. Okay, so now we have our initial concentration, and it's referencing the correct K value and the correct time value. Okay, great. So now we plot, this is our model. Okay, so now we'll plot our models. Model 1. Okay. So here's our chart. It's really busy, so it's hard to see what we're trying to do here. So let's change the chart type to a combination. Let's do, all the data will be a scatter plot. So let's change all the data to scatter. And then let's change all of these to a smooth line. Scatter with smooth lines. We will adjust all of these to be on the same axis, so we don't have multiple axes. Okay. Now it looks a little less busy. We can see the models are lining up pretty well with the data points here. Okay, so it says use the results in part B to come up with a good estimate for the value of K. Explain how you did it. Okay, so what we want to look at here is we look at these different K values, and you can see right away that this value is way different than these values. So that's an outlier. I would not include that into the average. So we can say that a good estimate for the K is the average of these three values. Something went wrong with lab 2. So that's a pretty good estimate for what K is, as far as we know. The reason why we're leaving this one out is because it's an outlier. If you did the calculation in part B correctly, one of the calculated values of K should be considerably out of line with the others. Think of as many possible explanations for this result as you can, up to 10. Okay, I can think of about 5, and maybe you guys can think of some other ones. I think 10 might be reaching, but I don't know, maybe they can come up with some other ones. Right off the bat, you can see that the initial concentration is way higher than starting with the rest of these. So that could be something that went wrong, that's significantly different. So different, maybe the reaction is not kinetically limited when the concentration of A is so high. You could also be getting like different things going on, different mechanics going on that change how quickly P is being produced. So you could also be getting like interference or something like that, if the concentration of one thing is too high. So anyway, that's a big thing to highlight there. Another thing is they could have had contamination in their experiment. Maybe when they started measuring at one point, they contaminated their sample, and that's why this measurement is way off. They could also have maybe just mislabeled, miswritten down, or started off with the wrong initial concentration. So maybe that was like an accident, and their initial concentration was actually significantly different. Maybe they didn't have their temperature correct. So they said that their temperature was at 275. What if their thermocouple was broken and it was actually at a different temperature? Maybe their equipment for measuring CP is not correct. And so, or measuring the concentration of A or P is not correct. Anyway, those are several different things. You just look at every single input into this function, see the concentration of P, the concentration of A, the initial values, the temperature, the time, each one of those things, the way you're measuring it, or differences between experiments in any one of those parameters, is going to potentially cause a difference in the result. So just pick one, time, pick temperature, pick concentration measurement, pick any one of those things, and you'll come up with several reasons why this result of lab 2 could be significantly different from another result. Okay, well, that is it for problem number 2.42. Thanks for joining me. If you need help on any problems from this book or another subject that I'm familiar with, if I have the textbook, let me know in the comments, and I will be happy to work on that problem for you and potentially make a video out of it. Thanks for joining me, and I hope to see you in the next video. Thanks. Bye.